We got to finish 5-2 to get on the line with the queue.
Okay, go.
Welcome to another live session for the online course, and the floor is open for questions on any topic.
Right, Matthew asks, my question is, do you think interstellar travel will be possible or plausible in the near future?
I would say in the near future, no, because space travel is kind of an ugly and difficult undertaking. I just learned a lot more about this than I previously knew by writing a book on the future of space travel called Beyond. Actually, it's coming out in a few weeks. And so I get into the issues of propulsion technologies and what we can do now and what we can do in the future and what's physically not possible. And the truth is the distances, of course, that are required are horrendous compared to distances in the solar system. Basically, compared to distances between the nearby planets, we're talking about hundreds of thousands of times further. And since interplanetary travel takes years, distance to Mars typically is going to take a year or so, you're talking about that factor more time to go interstellar at current speeds. So you either have to increase the speeds significantly, and that's enough to not violate a law of physics, so maybe some fraction of the speed of light, like 1 to 5%. But even that takes enormous energy to do so. So basically, the energy requirements for interstellar travel, even on a 1,000-year timescale, are prodigious. And this is just physics. There's no way around it. It's not a question of cleverness or, obviously a good propulsion technology will help, but you still have to get the energy from somewhere. So that's the issue. And the problem, of course, is the mass, that when you're sending people, I presume that was the intent of the question, when we're going to send humans, astronauts, space travelers, people have to be sent with, a complicated, expensive, large, and heavy or massive package of life support systems. And so a spacecraft that could travel to another star is going to be a pretty large beast. And so the energy requirement goes even not beyond that. Really, the only two ways around this issue are to not send us, but to send miniaturized robots, nanobots. And that technology is moving very fast. So nanobots will, of course, the mass going down means the energy requirement goes down dramatically by orders of magnitude. And those propulsion technologies of using, say, solar sails to get out of the solar system and then just coast at some significant fraction of the speed of light, and then essentially do the same thing in reverse when you get to the destination star system, that's entirely plausible. And that doesn't have to be that far off. I would say for sure within a century, maybe within 30 or 40 years. The other way to minimize the cost is, of course, to send the humans into a hibernating state where their life support requirements are minimized. And there would have, of course, to be some way to rejuvenate them when they get to the destination, and there'd have to be a way for them to live when they get to the destination. So that's only viable if you are pretty darn sure you have an Earth-like habitable planet waiting for you when you get to the other side. And even then, the technology of hibernation, of suspended animation, is probably, I don't know, a century away from being plausible. So that kind of a trip isn't going to happen anytime soon. It's really a stretch goal of technology to do interstellar travel, however you look at it.
The next question is from Stefan, and Stefan asks, when stars much larger than the size of our sun explode, they may generate a black hole. Would it be possible in the early conditions after the Big Bang that also black holes formed?
Yes. The speculation, well, there's a very esoteric theoretical speculation that the extremely early universe, I'm talking fractions of a second after the Big Bang, could have generated a sea of miniature micro black holes, microscopic black holes that are many tiny fractions of a gram or a kilogram, and those would have evaporated according to Hawking theory into radiation. So they wouldn't have survived much longer than the time they were created. That's pure speculation and theory. Less speculative is the fact that there has been hypothesized actually for several decades a population of stars they're called population 3, which is kind of illogical given that they're the first generation of stars to form. But they're the primordial stars, if you like, the first stars to form in the universe. So as the universe expands from a very hot, dense, and pretty much smooth state, gravity starts to form concentrations. And it's a matter of theory and some debate how long it would take for the first regions of gravitational collapse to cause stars to form. Some low estimates put that at maybe 50 to 100 million years, and longer estimates say it might take 200 or 300 million years. But it's around 100 million years, there or thereabouts. That's an era that's not accessible to us by telescopes at the moment. It's called first light, so it's a very exciting time in the history of the universe. In the theory of how stars form, because there are no heavy elements, the stars behave a little differently when they form. They actually form by very rapid gravitational collapse, and so very large stars can form, perhaps larger than we see around us, maybe up to 200 or 300 times the mass of the sun. And those stars would indeed die violently as supernova, thereby creating heavy elements in their death throes, ejecting them into space, the first heavy elements in the universe, and they would leave behind black holes. And they'd leave behind quite beefy black holes, perhaps 10, 20, 30 times the mass of the sun. So that is a pretty firm prediction out of theory, and simulations support it. So astronomers anticipate that first froth of pretty substantial stellar mass black holes would have formed in the very early universe. That's, when the universe, 100 million years is, of course, when the universe was less than 1% of its current age, so very early. And there will be a lot of them. Now, those black holes have subsequently not evaporated. That takes an extraordinarily long time, but in the history of the universe, it pretty much won't happen. But those black holes would have gradually aggregated into other larger black holes and settled to the center of galaxies, where, in fact, in the present-day universe, we still see them.
Okay, the next question is from Ellen, and it's timely. How does Ceres stay warm? Some scientists have speculated that the bright spots on Ceres are cryovolcanoes and contemplate the possibility of subsurface liquid water on Ceres. But if that's possible, then how does Ceres get its warmth? Since it wouldn't get tidal heating that the moons of Jupiter get, is it possible that it produces its own heat?
Yeah, an excellent question, because as the question alludes to, the extra ingredient of heating of the large moons of giant planets is tidal heating from those planets like Saturn and Jupiter. And that's what makes Io the most volcanic world in the solar system, even though it's a tiny moon. And that's, of course, what gives a lot of heating to the Galilean satellites of Jupiter. So Ceres doesn't have that. It is quite a substantial body. Obviously, it's the largest and first discovered asteroid, and it was found in 1801, I think, or 1800, in the search for what was the missing planet that was supposed to exist between the orbits of Mars and Jupiter. So it is quite a substantial object, a dwarf planet, if you like. And because it's substantial, it does have internal heating. So every rocky body has internal heating from natural radioactive decay, naturally occurring radioactive isotopes that exist in the Earth too, and give the Earth some substantial heating. So that's pretty much the only source of energy within Ceres so far from the sun, without a giant planet tugging on it. Is that internal heating sufficient to cause cryovolcanism and to have an internal ocean or a subsurface ocean that leads to geysers and hotspots? That's not clear. People are working hard to try and understand Ceres now. But really, there's no other source of heating, so it must be that. And it's only going to be tepidly active and episodically active. Ceres is not, overall active, and it's certainly not volcanic. So it has some very mild geological activity and some mild internal heating, which may create hotspots in very localized locations on the surface.
Okay, the next question is from Kurt. If two objects in a space otherwise devoid of references are each traveling towards each other, would it, at about half or a little over half the speed of light, would it not appear that to one observer on one object that the other object was approaching at the speed exceeding light?
Indeed, that's a classic framing of a question that's very important, that was very important for understanding relativity, for coming up with the theory of special relativity early in the 20th century. So in Galilean relativity, as it's called, the sort of relative motion of objects defined in the time of Galileo and then eventually becoming part of Newton's laws of motion, velocities simply add. I mean, they will add by vector addition because there's an orientation as well. But just imagine we're in a straight line linear situation, then net velocity will either add or subtract depending on the two velocities involved, and it's as simple as that. But as soon as light is involved, and as soon as the speeds become a significant fraction of light speed, then we're in the framework of special relativity. And special relativity has a simple mathematical form. Well, it's not a totally simple equation, but it's fairly simple, that describes how time and space are distorted by moving at substantial speeds. And so what happens is when a source of radiation is emitting, or when a source is moving and it emits radiation to the emitter, that radiation appears to leave at the speed of light, 300,000 kilometers per second, as you would observe on the Earth. And the Earth, of course, is moving, and it's impossible to find a completely stationary object in the universe, so the whole notion of stationary is sort of meaningless in modern relativity terms. Meanwhile, the person on the other source of radiation, or the other moving source, moving at half the speed of light, will imagine and measure their light source to leave at 300,000 kilometers per second. So how can they both be right? It's because the reference frame of one observer, when you connect that reference frame to the second observer, time is dilated, or time is stretched out, and so that makes the apparent speed of the other signal change for the second observer. So time and space are altered or supple on special relativity, and there's in such a way as to preserve the constancy of the speed of light, however it's measured, and by whomever, and whatever their motion happens to be. Which is a bizarre idea, but it's simply true. So the fact is that if two observers, as posed in the original question, were each moving apparently through space at slightly more than half the speed of light, and they measure the light signal from the other coming towards each other, they would still each measure that light to be traveling at 300,000 kilometers per second, because their time had been dilated or stretched out. So remember, speed is a distance divided by a time. So if you either compress distance or stretch time, you will alter speed, and you can alter speed so as to preserve the apparent constancy of the speed of light. Einstein elevated this to a hypothesis that the light speed was indeterminate, sort of independent of the motion of the observer, and experiment has amply confirmed it since then.
The next question is from Rod, and Rod would like to know, are we contaminating other planets with Earth germs from our probes that we're sending to Mars and other worlds?
Yeah, good question, because it's a legitimate concern. Do we have the right? There's an ethical and a political and a practical issue. The ethical issue is, do we have the right to contaminate other worlds when we might be altering them? If we imagine learning about another world like Mars or some other planet or a moon of the outer solar system is a scientific experiment, then you're clearly messing up the experiment if you contaminate that world. So it's a bad way to do science to cause contamination. The ethical issue is, do we or does anyone have the right to alter another world by our efforts, by perhaps our careless or negligent efforts? And since space is not owned by space objects, Mars and the outer moons and so on, are not owned by anyone, any one person or country or organization that's contaminating or changing a world is sort of violating the ethics of space by doing that arbitrarily and unilaterally without consulting anyone else. So that's the problem. And then, of course, it becomes a political issue too, because only a few countries are even able to do this. There may be a lot of countries in the world that say, well, we don't want Mars altered. You should leave it pristine. You should take extreme care when you send a space probe. But if those countries are not doing the activity, it's sort of the argument really comes down to those who can do it. NASA has evolved in this. So NASA has always had the issue of contamination in their heads, but mostly that issue of contamination has been backward contamination. That's contamination of the Earth. So when the Apollo rocks came back, they went to a secure facility in Johnson Space Center that I visited. It's quite impressive. There's 360 kilos of moon rocks there, which is almost all of them. It's a level 4 biohazard containment facility. It's extremely high. There's only one higher level, and that's sort of through the roof on security. They can handle Ebola or anything in the Johnson Space Center. And that's the place where the moon rocks have been kept in a pristine and extremely safe environment for the fear of contaminating us with moon germs. Now, we think the moon is sterilized and not living at all, especially at the surface, but they took no chances. And we've had Mars rocks. We've had sample return from a comet. The Stardust mission brought back comet material, and that comet material was raced in a triply insulated, vacuum-sealed container from the recovery site straight to Johnson Space Center, to that same facility. So NASA's been extremely cautious about objects that come to Earth, not the naturally occurring ones, the meteorites, which essentially get sterilized by their passage through the atmosphere, but any material we've brought back here. The forward direction they've been less concerned with until recently. So I'd say in the last decade, NASA's been sensitized to the fact that we've left debris on the moon, we've left debris on Mars, we've, in a much more modest way, traveled in the outer solar system. And the current protocol really does call for current and future Mars missions to either clean up after themselves or be so designed as to be sterilized when they enter the Martian atmosphere. And the Martian atmosphere is 1% of the Earth's atmosphere in pressure and thickness. So even fairly rapid passage through the Martian atmosphere is not completely guaranteed to sterilize a spacecraft. And of course, it won't sterilize interior areas where the rover might be. So Mars has actually taken some trouble to sterilize its rovers or its landers in advance of their launch, and then keep them in a secure condition before launch, and then the spacecrafts themselves are sterilized too. So NASA's sort of done a good job in the last 10 years of trying not to contaminate Mars with our debris. Now there's junk, there's trash left behind. The rovers, when they die, will just sit there. They won't rust, of course, there's just not enough water to rust them. But we are leaving some junk behind, but actually we're trying fairly hard not to contaminate Mars with life or just with debris.
Okay, the next question is from someone online now, and they want to know about the possibility of a meteor. What is the risk of a meteor hitting the International Space Station or any other satellite, and how is the orbit of a satellite determined?
It's a real concern. The probability of these will be micrometeorites or micrometeors. They're pretty much small. They're traveling extremely fast at 10,000 miles per hour or in excess of that. And so even a gram or a dust grain sized particle can puncture the hull of the International Space Station. And the odds of that happening are significant. The space station is in a reasonably high orbit, about 360 kilometers, and so that's high enough to be above a lot of the low Earth orbit satellites. So most of the space debris is in the lowest of the low Earth orbits, 100 to 150 miles. It's where the place where all the satellites are, and a lot of these degraded satellites and have collided with each other, and a few have been destroyed, and the debris just keeps getting worse and worse. So if you want to be safe, and a spacecraft or an astronaut will really not be safe for any length of time in those low Earth orbits. So you really have to go to a much higher orbit where the space station is, and where the shuttle, of course, went most of its time, to minimize that impact risk. But you don't take it to zero. It's still significant. And I think various studies from NASA and the European Space Agency suggested that over a 10-year period, the odds of a rupturing, not a catastrophic destroy the space station impact, but a rupturing the skin significant impact to the space station was of order half or 70%. In other words, it's going to happen. It hasn't yet, but it's very likely to. Geostationary orbit is higher still, and there it's pretty pristine. There's not much junk up there. But the junk can only get worse. There's really no way of cleaning it up, and that's one of the problems. That's why it's become a political issue, because as more and more, not just countries, of course, but commercial entities put up satellites and spacecraft, and they die, and they occasionally hit each other and break apart into tons and tons of shrapnel, traveling at very high speeds, it is going to become a real issue. And basically, humans are not going to want to spend any significant time in the lower echelons of low Earth orbit.
Okay, the next question is about simulations in astronomy, and they want to know how that is done. We've seen a few interesting examples of computer simulated experiments. Could you speak more as to how they're made? Do astronomers develop the software, or do they farm it out to computer scientists?
Yeah, it's a good question, and I like the question because nobody's asked about this before, and it is a significant part of astrophysics now, of the modern subject. And in fact, just being broad about this, I would say that modern astronomy or astrophysics is a three-cornered hat or a three-legged stool. Historically, especially in my subject, cosmology, the interplay was between theory and observation. The theory would be general relativity, the theory of the expanding universe and its constituents and how mass and space and time are distorted. And then the observation would be of galaxies or supermassive black holes or other objects in the universe or the curvature of space, whatever you could measure. And the entire subject was based on matching the observations you could make, counting galaxies, measuring space-time curvature, with the predictions of the theory, the Big Bang and general relativity. Modern astrophysics has this third leg, which is simulation. And why simulation is important in the first place is that the universe is complex. And so sometimes the simple theory does not accommodate what you're actually observing. In fact, cosmology is a really good example because the simple theory of general relativity applied to the expanding universe specifies essentially the metric, which is the space-time, the mathematical expression or description of the space-time as it expands, and it does not relate to anything within the space-time. The objects within space-time, like galaxies, distort the space-time, bend it. And so actually the backdrop theory is based on not having any objects at all. So it's a sort of it's an artificial approximation. In simulations, you can make things by gravity. You can put in particles and watch them cluster over time into objects like galaxies, and you can put in general relativity as well. So you can model space-time curvature and the expansion and the creation of objects, and you can even hope to get the properties of galaxies out at the other end. So simulations in cosmology, of which there have been a few in the course, or there will be, are very powerful because they include the full complexity of the universe, and yet they're not giving short shrift or mistreating the theory. The theory is in there too. So they allow a more sophisticated comparison of theory and observations than would be possible if all you were dealing with general relativity and expanding universe model. And the same is true for stellar astronomy. So in stellar astronomy, the astrophysics is fairly complex, and our simple theories of stars describe how their temperature, their density, and their pressure vary with distance from the photosphere. They involve calculating reaction rates of the fusion reactions in different zones. And those theories are fairly well developed and were first put in place in the 1930s and 40s. But the astrophysics of a star is fairly complex. It's a mixture of convection and radiation. Neutrinos and other more esoteric particles have an important role in energy transport and in how the structure of the star is. And then when the star goes through transitions, that is, episodes of activity where it transitions to a new nuclear fuel, or it runs off the end of its nuclear fuel and goes to a planetary nebula or more dramatic end state, then actual simple theory is inadequate to calculate what's going on. You essentially have to turn to simulations. So the only plausible descriptions of a supernova come not from simple theory, math that you could write on the back of an envelope, but from supercomputer simulations. And that was one of the first uses of supercomputers in the 1970s in astronomy. So in almost every field of astrophysics, simulations are really important. And they're so important now that they're just part of the wallpaper of astrophysics. They're done in almost every subject, planet formation and whether there'll be water or habitable zone or geological activity. So it's planets, stars, galaxies, cosmology. The whole subject is now rife with simulations. They're only as good as your assumptions and as powerful as a computer you bring to bear on them, but they're extremely valuable. The only downsides of this new world are that people can trust their simulations a little too much. The truth is, we have to tether everything in observations. The simulations are so amazing, they're so fully fledged and fully featured that you can observe the simulations. People use that verb. I'm going to go and observe my simulations and extract observational parameters from them. But that's, of course, not the same as observing, and people doing that always need to remember that observing is observing and simulating in a computer is something else. But it's extremely powerful, and I would say this triumvirate, this three-cornered stool of observation, simulation, and theory, has really moved the subject of astronomy and astrophysics along very fast in the last few decades. And it's only getting better, of course, because the computers, what used to be done with in the 1970s with the supercomputer at, say, Los Alamos, the weapons lab, the biggest and most powerful supercomputers have always been in places like government labs and weapons labs. And astronomers used to try and get time on those on those computers. And it took those kind of computers to do the calculations. Now, what could have been done 30 years ago at Los Alamos in their biggest computer can be done on a desktop cluster for the hardware costing maybe $10,000. So the bar has come down enormously. So you can do simulation astrophysics with very modest hardware, or modest priced hardware. The hardware is incredibly impressive, of course. And to answer the part of the question about who does this and how is it done, that's interesting too. The culture of astronomy has changed. And so in parallel with the emergence of simulations as an important part of the subject, there's now a cadre of professionals in astronomy whose skill set includes astrophysics and astronomy. They probably went to grad school in astronomy and have a PhD in astronomy, or perhaps physics, and moved into astronomy. But their skill set now is heavily involved around programming and computation and writing code to do these things. And so there's a specialty now of simulation astrophysics where the people doing this are, basically the skill set involves parallelizing your code. So to run, especially a cosmology simulation, you have to do enormous numbers of parallel operations. And the architecture of running an astrophysics simulation is rather different from the architecture of, say, doing a billion simple bank account operations. So it's a much more sophisticated level of programming, and that's a very specialized skill set. It does apply to other fields, so people who do this are going to be good working on weapons or working on the weather or actually modeling financial markets or some other areas. So that skill set can apply in other domains. On the hardware side, the hardware has also become specialized, and some astronomers or computer scientists have got involved, and they have actually custom built hardware to do these jobs better than a standard computer would do. It's not really the right thing to do to just go and buy a fast, blazingly fast PC, high-end laptop or desktop, or 4 or 5 of them, and just string them together and expect them to do a good job. What's happening now is that people are custom designing chipsets and circuit boards to parallelizing the hardware of these calculations. And so the hardware to do simulations is really quite specialized now, and there's this whole niche of developing the hardware. So I'm glad for this question because it's a part of the subject that doesn't often get noticed, in fact, but astronomers are very well aware of how important simulations are.
Okay, the next question is, exoplanets that are far from a star take longer time for their orbit. How can we be sure that it is a planet determined from a Doppler effect from just one pass?
It's a good question, and the answer is you can. The Doppler method, as in the transit or eclipse method, has to be based on repeatability. So the signature of a Doppler detection of a planet is a sinusoidal variation of the Doppler shift of the parent star caused by the tug of the planet. And as the questioner implies, these planets are going to follow Kepler's laws just as the planets in our solar system do. And so their periods, if they're far from their parent star, will be very long. And so the practical problem there is that it takes a lot of observation to measure a complete period. Clearly, an exo-Jupiter in a Jupiter-like situation around a sun-like star far away, it'll take you 12 years just to get a Doppler curve. This impacted the subject significantly until fairly recently, because the first exoplanets were only discovered slightly less than 20 years ago. And for a long while, nobody had a decade's worth of data. And so even in principle, you couldn't detect a normal Jupiter because you just didn't have enough data to sample a full curve. And in truth, to be truly confident of an exoplanet detection, you probably need to measure to full orbits that you can then map together and collide and increase the signal. So it's only recently, with 20 years of data in the can, that people have started to be confident in talking about these more remote planets with longer orbital times. They do exist, but the statistics are not good enough to say whether there are a lot of normal Jupiter and Saturns out there analogous to our solar system. So that's actually a limitation. The very long times required to observe these things.
Okay, the next question, is there really diamond rain on Saturn? If it is real, why don't we go there and pick them?
Well, yes and no, diamonds. It's a little tricky. So people make descriptions of the various states of carbon, and they analogize them to diamonds. And the analogy is not always correct. For instance, people have analogized the white dwarf state of a carbon-rich star, a carbon-rich white dwarf, as being like a diamond material because it's a quasi-crystalline state of nuclear matter based on carbon. But that's probably a big stretch to call a white dwarf a diamond. These crystalline forms of carbon that might have emerged in the atmosphere of a giant planet, they're not as strictly regular as a diamond lattice because of the way they form. They're a little more chaotic. They're sort of semi-amorphous, I guess is the technical term. And so they're only semi-diamond-like, if you want to put it that way. But they are crystalline forms of fairly pure carbon that are cousins to diamond, if not brothers and sisters to diamond. And then to answer the other part of the question, should we go and harvest them? And the answer, maybe some time ago, the answer might have been yes, but actually the ability to create diamonds industrially has progressed a huge amount in the last few decades, creating the temperatures and pressures sufficient to create a diamond on Earth in the lab. It's much easier to do, so therefore it's not cost effective to go and harvest the quasi-diamonds from Saturn.
Okay, the next question is very interesting. With evidence supporting that our planet is indeed facing through global climate change, I was wondering if there was any evidence of climate change on other planets. For example, Mars and the disappearance or lack of water.
Absolutely. So I was hoping this would come up, and if no one had asked it, I was going to talk about it anyway. So the big discovery, it's not a recent discovery, but it's a very important paper published by a large group out of NASA of this past week, has been, of course, the evidence and the discussion of ancient oceans on Mars. So we've had a long suspicion. So to answer the question that was posed, yes, climate change on planets is not only possible, it's likely, and it's almost inevitable. So we know there's been substantial, let's just start with home, regardless of what we do to our planet, the atmosphere and conditions of the Earth have changed enormously over 4.5 billion years. Because clearly at the beginning, the Earth didn't have any oxygen that was produced by microbes starting 2.5 to 2.7 billion years ago. So the first atmosphere of the Earth was completely different from the atmosphere today. It had no oxygen, had a lot more carbon dioxide. It had a roughly similar amount of nitrogen, and it had other components that it doesn't have now. So the atmosphere of the Earth has evolved substantially over cosmic time. The atmosphere of Mars has had even more dramatic change, and that was the basis of the announcement last week. Let me just back up and say what the discovery was, since I'm sure most of you have heard about it, or you've seen these evocative artist sketches of Mars with its North Polar region covered with water. It's a very elegant technique. It was done not by the rovers, the science group are all involved in those Mars rovers. Mars is what they do. But to do this measurement, they used ground-based telescopes and infrared measurements. And basically what they did was they measured the variation across the surface and over time, modest amount of time, of normal water involving normal hydrogen and normal and heavy water, or deuterated hydrogen. So that extra neutron involved in the heavy form of hydrogen increases its weight. And on Earth, the ratio between the heavy form of water and the normal form of water, I think there is a factor of 10,000 in difference. It's heavy water is 1 part of 10 to the 4, 0.01% of Earth water in the ocean. It's very small, so it's a trace. It's very easy to detect both of these components remotely using infrared spectroscopy, remote sensing, and a large telescope to disperse the light into spectrum. You can pick out the heavy hydrogen in the water and the regular hydrogen, normal water. And when they did this on Mars, of course, the key ingredient here is that thinking that Mars has gradually lost its water into space by evaporation into space, which will happen because Mars is substantially less massive than the Earth, so it can leak off these heavy molecules that will be retained on the Earth by its gravity. The diffusion rate or the leakage rate clearly will depend on the mass of the molecule. So the deuterated form of water will diffuse at a lower rate than the normal form of water, just because it's more massive, it has that extra neutron. And in fact, that leads the Mars ratio of deuterated to normal water to be very dramatically different from the Earth. So that is beautiful and a simple measurement. Not only that, you can then work backwards from the very different diffusion rates of these two components to project back how much water Mars must have had. If you imagine that at one point it had a normal 1 part in 10 to the 4 ratio of these two, and it just gradually lost a lighter form of water preferentially. So that's the calculation these people did, and the result was quite dramatic and fairly convincing. Most of the community thinks this result is very solid. They were then able to use these diffusion rates to project backwards to the fact that the Mars polar caps that we see, the water embedded in those polar caps, which also includes a lot of frozen carbon dioxide as well, there was roughly 6 times more water when this whole process started 4 billion years ago. So Mars has lost roughly 85% of its water into space. That's quite amazing. And it's left Mars with these little shrunken ice caps that also shrink and grow during the Martian season, because Mars has a similar orbital tilt to the Earth, so it has seasons like the Earth's seasons. So if you run these numbers backwards, you can say how much water Mars had at the beginning and what that accounts for. And the answer is substantial. I mean, it's roughly 100 meters of water across large parts of Mars 4 billion years ago. And that amounts to a shallow ocean. And the reason the ocean aggregates in the northern hemisphere in those artist drawings that you've probably seen on the web is that Mars has a rather strange geography. As a small planet, it has some substantial mountainous regions and volcanic regions in its southern hemisphere, whereas its northern hemisphere is mostly sort of lowland plains. And so, given the way gravity works, whatever water Mars had would have aggregated by gravity to the lowest points, which were mostly in the northern hemisphere. And that's why Mars was speculated to be covered roughly 20% by water, most of which was in the north hemisphere, making a rather strange look at a northern ocean where there was nothing in the south. So that's amazing. That's a beautiful piece of work to talk about the Martian ocean that long ago. But the other thing it does is it changes the timelines, because by drawing back when Mars had an ocean that was that substantial, and knowing how quickly that ocean has evaporated and turned Mars into a cold, arid place that it is now, the span for which Mars had surface water and was potentially habitable has grown from what astronomers thought might only be 1 billion or so years to 2+ billion years. This process, of course, was gradual, but it's likely that Mars had substantial standing water, starting with this huge ocean and gradually shrinking into shallow seas and then puddles, I guess, and the rivers dried up and then it went arid for over 2 billion years. That's a long time, and if all the ingredients were there for the biology, then Mars could clearly have got started with life around the same time the Earth did, which is 500 million years after formation, so 4 billion years ago, and Mars could have been habitable or could have hosted microbial life for close to 2 billion years or maybe more, until the life died out because everything dried up and it presumably couldn't survive as the atmosphere thinned out. So that's extraordinary, and it really paints a totally different picture of how a planet can be really habitable for a couple of billion years and then go uninhabitable, for which is what we see Mars as now, or barely habitable. If Mars is habitable, it's under the surface in aquifers.
And the next question is from Esteban. Why, if LIGO is ready to work in 2014, won't the first detection of gravitational waves be until January 1st, 2017?
Yeah, LIGO, they're working hard and flat out. It's had some obstacles to overcome. They had a large test run, as I'm sure you know, taking test data, and they met most of their design goals, but not all. So the technical spec on LIGO is extraordinary. I mean, it has to detect essentially variations in a dimensionless number that sort of relates to how much a space-time distortion is caused in a meter-length object by the passage of gravity wave by 1 part in 10 to the 20 or so. It's an incredibly accurate experiment. It's the most accurate physics experiment ever by orders of magnitude. So as they came out of their test phase, LIGO was going to retool to go into its science phase with 10 to 30 times better sensitivity, which would allow it to detect supernovae and cataclysms in the nearby universe and do real science. But it's not been completely smooth. They've had some technical issues, some really mundane technical issues of noise in the detectors and stochastic variations in some of the mechanical components that map into noise in a gravity wave detection. They've had a few funding issues, even though they're a fairly well-funded project. Their marching army of engineers and scientists has had to shrink a little bit based compared to what they hoped they would be able to do a few years ago. And so for those technical and financial reasons, they've sort of shallowed out their timelines, and that's why we're seeing a year or two delay in when they think they'll take science data. But none of these are showstoppers. The project has essentially irresistible momentum. It's one of the most exciting experiments on the horizon in astronomy or physics. The talent involved in that team, that collaboration, is formidable, and they will be able to do what they claim they're going to do. And even these technical issues are in the margins, if you like. They're not fundamental to the detection. So they may not have exactly the sensitivity they scoped out or spec'd out 10 or 15 years ago, but at worst, it's going to be a factor of 2 worse, which won't stop them doing science at all.
The next question is from Vincent, and Vincent asks, hello, when the sun turns into a red giant, when will that happen, and how far will it be from the sun to the Goldilocks zone?
So the model of the sun is fairly robust. It's based on stellar evolution theory that we've had in the textbooks for 70 or 80 years. But still, it's not a precise science of prediction. So the duration, the sun is roughly halfway through its life, and I think the best models suggest that the time to the red giant phase is about 4 billion years. But that's 4 billion years plus or minus 100 million or so. So it's not a super precise number. So in about 4 billion years, the sun will inevitably transition into a new phase of nuclear burning, because as the hydrogen is being mixed by convection, but as the hydrogen is mostly exhausted, it never gets completely used up, the sun will lose the pressure support in its core, and so gravity will force it to collapse into a new energy state, at which point a new fuel can be ignited, and of course that's the helium that's been creating all this time, turned it by the triple alpha process into carbon. Meanwhile, hydrogen fusion will continue in an outer layer, and the reconfiguration of the sun into sort of shells will create a red giant phase where the outermost cool envelope, because of this extra energy from the new nuclear reaction, is puffed out into a large diffuse cool envelope. And so that the photosphere that has a temperature now 4,800 Kelvin, sufficient to make it a yellow star, will cool substantially to 3,000 Kelvin or so, making the sun appear as a red giant, even while the core is hotter than the sun's core now. That giant envelope, by the various calculations, I've seen different versions of this. So most of the calculations predict that it will reach close to the orbit of the Earth, and some predict that it might even get out as far as a Mars orbit. It's very diffuse, so there's no sharp edge to this outer envelope. But clearly, life on Earth will be extinguished at this point, because the luminosity of the sun will increase, and if you don't want to be in the envelope of the star. place to be. So the Goldilocks zone, it may not actually exist. The Goldilocks zone will probably move into the outer solar system, possibly around the orbit of Saturn. So if I were going to make a recommendation of buying property, I'm not in the financial markets, but Titan is a pretty good bet. It's possibly habitable. It's extremely cold now, but it'll be probably a nice place to buy real estate for that future eventuality. It might be in the Goldilocks zone. But that Goldilocks zone isn't going to last too long, because the red giant phase is a much shorter phase of evolution than the main sequence of the sun, which in total will last almost 10 billion years. So the thing will change again, and of course the final outcome, there'll be a planetary nebula, which will once again destroy biospheres throughout the solar system, and then the final state of a cooling ember will create a habitable zone, if you can even imagine it, that's shrunk incredibly close to the dying star to get enough energy to sustain life. So either way, basically the bottom line is that when the sun leaves the main sequence, which is the phrase for it exhausting its hydrogen, is not going to be a happy situation for planets and life in any solar system.
Julia would like to know, do you think sending a probe or unmanned spacecraft to explore the Kepler exoplanets will be possible in the upcoming years? How far are we from reaching that point of space exploration, considering how far we are from them?
I think it's tough. So the first question about interstellar travel, which I answered, really was relating to the nearest stars. So everything I said about how hard it was related to stars that were maybe 5, 10, 15, 20 light years away, the nearest stars. With Kepler targets, it's even worse. So those are the nearest Earths, the nearest known Earths. And Kepler, because it was a small telescope with a small field of view, was only able to look at a patch of sky and 150,000 or so stars down to a fairly faint level. Most of those stars are not visible to the naked eye. They're roughly 100 times fainter than the eye can see. And they're much fainter and further away. They're much further away than the stars you could see with the naked eye in the night sky. And the typical distance to Kepler exoplanets is a few hundred light years, and some are a few thousand light years away. That's still the neighborhood of our galaxy, which is 100,000 light years across. So that's still in our sector of the galaxy near the sun. But it's by no means the neighborhood of the sun. And so distances of hundreds of light years are really formidable. So if it's really not imaginable even much within the next century to go to stars that are 5 or 10 light years away, going to those that are hundreds of light years away is just not going to happen on any reasonable time scale. They're essentially beyond reach.
Okay, the next question is from Patricia. Does anyone know or have a theory as to why atoms in the universe are mostly empty space?
Well, the theory of atoms and the discovery of empty space was by Rutherford, of course, in the 1920s and 30s at Cavendish Lab in Cambridge, England. They had very elegant experiments that showed this hard nugget-like nucleus with most of the mass, 99.9% of the mass, surrounded by a cloud, a diffuse cloud of very light electrons. And in those days, before the quantum theory was fully developed, nobody really had any idea why in fact, it was before the quantum theory, it was predicted based on classical physics that the atom should collapse. This was considered a huge problem in the 1910s and 20s, that if you just took classical physics and applied it to the situation of a positively charged nucleus and negatively charged electrons orbiting, as they thought in those days, around it, then the atoms should decay on timescales of nanoseconds. So matter should be unstable and everything should just collapse, fall into a pile. And then there would be no empty space. It would just be super dense matter as it all collapsed. Well, that clearly didn't happen. And so the quantum theory, essentially by providing these quantized energy levels, which included a ground level or a zero level energy state, sort of provided the prohibition from atoms in the theory. In the quantum theory, it amounts to a prohibition on atoms from just collapsing into a pile of super dense material and ruling out these large spaces around them. The quantum theory put a prohibition on that, and it also described the probability state of the distribution of electrons. It could give you a situation where you would have a 10% probability of observing an electron this far from the nucleus, or 2% probability this other distance from the nucleus. And that discreteness of energy levels and these quantum rules also coincided with the size of the atom. So we had a theory that said why atoms, the full size of a neutral atom, is the size it is. And that size, of course, accommodates a situation of almost entirely empty space because the nucleus is a tiny, tiny fraction of the volume of those atoms. So it's really the quantum theory that explains why matter is mostly empty space, and also why matter just doesn't collapse and stays puffed up, if you like, or buoyant in this mostly empty configuration. Now, is that a good enough explanation? Maybe not. Some people, and philosophers and physicists, have critiqued the quantum theory for not being very intuitive or not being very reasonable. And the only rebuttal from physicists is, well, it works. It works almost perfectly. It describes everything we can do with atoms in the lab and interactions and energy states and spectroscopy and so on. So physicists have essentially sort of given up on trying to expect atoms to be intuitively sensible entities, and they're just happy to work with a theory that explains them very well.
And then Stefan would like to know, building on that, what is space? Is it a field? Can it be considered just part of a geometry, equation in physics? Is it kind of ether?
So it's a great question, because the fundamental questions are always the most interesting, because they're hardest to answer. It's easier to say what it isn't, and so of those few things you mentioned, it is not an ether. So that was the classical physics supposition, that the space couldn't be actually nothing, that vacuum didn't really make sense, so there had to be an ether, both for electromagnetic waves or radiation to travel through. If electromagnetic waves are waves, and what's doing the waving? That doesn't work or make sense if it's a vacuum. So they hypothesized an ether for that, and then as soon as you have an ether, the ether, however hard to detect or however evanescent it is, becomes the medium within which you can measure and define space. So that's comfortable. I mean, that's a comforting construct to have theoretically, an ether. Unfortunately, the Michelson-Morley experiment in 1895 in physics demonstrated that there is no ether, that the Earth does not move through any ambient medium like an ether, or a reference frame with respect to which we can measure speeds and so on. With no detection of an ether, we were left back with the vacuum, that space is a true vacuum. Then the theory of general relativity came on, and general relativity posits something called space-time. So space-time is a coupled entity. So we're now, with general relativity, we were now told, or we now had a theory that worked really well, passed all its tests, that no longer had space as absolute and independent of anything else, as it was to Newton, but as something that was coupled to time, maybe another difficult to understand thing. So whatever space is, it's not really pure space, it's space-time. It's more appropriate to think of space-time as the entity, whatever that might be, rather than pure space. So it's not a field, it is a coupled entity called space-time, and beyond that, it's rather hard to say, because the vacuum is a very rich concept in physics. Things can happen in a vacuum, basically in nothing. You can borrow energy from the vacuum, you can create pressure from the vacuum, you can do all sorts of interesting things from vacuum states in physics. So nothing is not quite as boring as it used to be, thanks to quantum physics and more modern ideas. But that is the best way to think of it. And space is built into these theories in a very direct way mathematically. So perhaps the simplest answer is the geometric answer, that since general relativity is a geometric theory, then space is a geometric construct.
Okay, Benjamin would like to know, I heard an interesting theory related to the dark matter debate. It was suggested that there isn't any unexplained gravitational interaction, but rather vast undetected electromagnetic fields that are responsible for holding galaxies together. Do you think that might be possible? How would we test such a theory? And then several people have had questions about dark matter. So if you could just kind of talk about what we know about dark matter.
So without a dark matter particle having been detected, there are other theories on the table, and the sort of electromagnetic field idea that you're talking about is one of those, a raft of theoretical ideas that are in play. Even sometimes to their practitioners, the ones who are talking about them and writing papers about them, they're considered sort of fringe theories. They're alternative hypotheses that are worth playing out. I mean, theorists like to be clever. They like to be aggressive in trying to understand nature, and the progress has been rather slow in figuring out what dark matter is. So theory is speculating quite actively right now. That particular variant on theory, I don't think has any direct evidence to support it. The best hypothesis, so just to cut to the chase, because there are all these alternative, sometimes fringy theories, the current best hypothesis is that the dark matter is a fundamental subatomic particle that's not yet been seen in the physics lab, for the simple reason that it's extremely weakly interacting, which is why it doesn't have electromagnetic interactions. It doesn't emit, absorb, or scatter light, which is part of why it's so hard to see, find, or detect. And yet it's quite an abundant and massive particle. We know it has to be abundant and massive individually as a particle because the dark matter outweighs normal matter by a factor of 6 in the universe. That is to say, dark matter, protons and neutrons, that is. So whatever the dark matter particle is, in number times mass, it amounts to 6 or 7 times more than the sum of all protons and neutrons in the universe. That's what we know by observation. And the kind of theoretical particle, or particle in theoretical physics, that can match that requirement are quite limited. So the best candidates have and continue to be supersymmetric particles. So one of the goals of physics is to unify these rather disparate particles we have in nature, which are fermions and bosons, that is, integer and half-spin particles that really behave quite differently. They're just like different categories of particles. They have different statistical properties too. And so that dichotomy of the particles in the universe has always been puzzling to physicists who want sort of everything to be unified and the same. And their way of unifying them is to hypothesize some supersymmetric parent particles where these differences in properties sort of go away. So as the price of making a unification of the fermions and the bosons, you have a supersymmetric suite of particles. And the most massive stable one in the theory turns out to have about the right properties. It's fairly abundant and it's fairly massive and it doesn't interact with electromagnetic radiation to be the dark matter particle. There's not a single candidate in a sense because there's a series of related theories of how to do this. So it's not quite as simple as one candidate, and if we confirm or deny it, we confirm or deny the theories. And in fact, CERN has not smiled kindly on supersymmetric theories because the last 2 years of the Large Hadron Collider, which successfully detected the Higgs particle, have not detected hints of supersymmetry where they were expected. So the lack of supersymmetry evidence from CERN in the last couple of years is unnerving people because it's taking away or pushing back their hope for detection of the dark matter particle. Meanwhile, independent of the accelerators, there's a set of physicists who have experiments in deep mines, typically a large solid-state detector like a huge lump of ultra-pure silicon or germanium, where they're trying to look for the dark matter particles, which of course exist throughout space and are passing around the Earth and through the Earth and all around the solar system. They are trying to look for the rare collisions of those dark matter particles with the detector. And since the dark matter particles don't emit or absorb radiation, these are not light or electromagnetic interactions. These are literally collisions. They're resonant collisions, releasing collision energy in the detector. So you need ultra-pure detectors. You need to shield from all the contaminating other heavy particles like cosmic rays, and that's why they're in deep mines. And those experiments are well designed and should produce a result within the next few years. Some have already started making interesting limits. So the jury is still out on whether this particle candidate for dark matter, even though it's not one candidate, it's sort of a related set of cousin predictions, is right or not, but we'll probably know the answer within a couple of years. And if the answer is no, if the answer is none of these CERN nor the mine experiments can find a particle with the right properties to be dark matter, then all bets are off. Then the theorists will go wild because they will have to come up with new ideas.
That's the end of our time for today. Thank you all very much for joining us.
Okay, thank you. And we'll do this again next week.